So today we are going to be looking at a new law that we can use to solve our equations. It combines all the past laws, Avogadro's, Charles, Boyle's law. For this law to work though, you need to understand and assume some points. This law works with ideal gases, which are imaginary and work under very specific conditions. First, the gas must be made up of molecules. If I can find my cursor, there we go. Are made up of molecules that go in completely random and straight lines, even though these are not very straight. It's completely random. It's undetermined by anything. It's not affected. You must also assume that pressure is due to collisions between the molecules, as you can see here, and between the edges of anything in the container. Between the container, I suppose would be the best way to phrase that. Between the container. So here we go. If it's hidden off the container, it's going to create a change in pressure. Thirdly, all collisions between the molecules are perfectly efficient. So if these two molecules collide on their way, nothing's gonna. It's gonna be perfectly elastic and efficient. They're just gonna bounce right off each other with the same amount of kinetic energy that they had coming in. So they're 100% efficient. Fourthly, the temperature of the gas, whether it's in Kelvin, is directly proportional to the kinetic energy for whatever reason. I can't remember if that's the way it is or if it's E, a K. I believe it's that. That's more correct than this. Sorry, did it wrong. That's my bad. Anyway, lastly, maybe most importantly, is that it's assumed that there's no intermolecular forces between the molecules. So if you have two in a container, and say these are just, passing by each other, there's going to be no bond between the two on the way by each other. Like when they meet, at this point of no return, in the real world, they would begin to bond to each other and be attracted to each other. But in these ideal conditions, that's never going to happen. They're never going to bond here. They're just completely unattracted to each other, and that's all. Like they're not attracted at all. So now that we've covered the kinetic theory of ideal gases, let's move on to analyzing the equation itself. The ideal gas equation is as follows. It is PV equals nRT. So each of these variables has a different unit associated with it, so let's go through this. P is kilopascals. Actually, I should list out what all these are. So this one is pressure. This one is volume. This one is moles. This one is a new constant that we'll learn. And this one's the temperature. So the pressure is shown as kPa. Volume is measured in liters. Moles is obviously measured in moles. R, our new constant. You need to remember this. It's not on any kind of test, or it is on every test, but it's not written down on a cheat sheet or anything, so you just need to remember it. But it's very simple. 8.314. I always remember this. This is a terrible theory. I apologize. I always remember this as 314. That's pi, so that's very simple to remember the decimal places. You just need to remember the 8, which is very simple after a couple questions. And the units for this are kpal over milk. This is how I remember it. My teacher taught me this way, so it's just the easiest way to remember it. But the actual units are kilopascals times liters divided by moles times Kelvin. So, and then the last unit is temperature, or the last variable is temperature, and its units are Kelvin. Right, so utilizing this, let's do some sample questions so I can show off the unit analysis and the simple calculations involved. So let's start out with me typing up the question here. Erase all of this. Alright, so the question is, what is the 1,000 liters of nitrogen at SATP conditions? Right, so what is the mass of 1,000 liters of nitrogen at SATP conditions? So the first thing, just put an S and this. There, that's better. Alright, that works. Alright, so the first thing we should do when we get a question like this So we need to write down all the variables that are given to us. So we know we have 1,000 liters of nitrogen. So this is going to be our volume. We know we have SATP, and we know SATP is 100 kPa. And we know that our temperature is 298.15 Kelvin. Alright, so now we just need to fill this in. Let's just make a list and go down. So the pressure we know is 100 kPa. We just wrote this here. So we should know by now. Our volume is 1,000 liters of the nitrogen. Our moles, we don't know this yet. This is our unknown. This is the only variable that we haven't been given in this entire question. So this must be what we're trying to find out. And then our constant, this is a terrible R, I apologize. There. Our constant is 8.314 kPa over milk. Remember, just think of pi and then with an 8. And the temperature, we know because we just said it, is 298.15 Kelvin. Alright, so let's write out the formula. We know with this current formula that this is not going to help us. I mean, this determines nothing. This determines what P times V is, and that's proportional to the moles times the constant times the temperature. But this means nothing to us. So how do we fix this so that we can determine the number of moles? Well, what basic science 10 and probably behind, or I guess inferior to that, has taught us is that we need to isolate for the variable that we want to find. So we know we want to find n here, which means we need to get this out of the way. So what we do is we need to divide this out. This is how we've been taught. This will cancel the units out, right? So if we're dividing by this r, these units are going to cancel out. There's no more r on this side. But we know that what we do on one side of the equal sign, we need to do to the other. So you have PV over here. You go like this. So it's not PV divided by r. And it's now not on this side. We need to do the same thing to t. So these divide each other out. We need to do the same thing to the other side. And we're left with PV divided by RT equals n. Alright, so now that I've shown you this, and it's been written out, let's sub all our variables that we already know into the equation so that we can determine what each moles are. So right, so we start off with 100 kPa times 1,000 liters. Remember, PV over RT. And then we come down here, write out a constant, 314 kPa over milk. Make sure you put brackets, this indicates multiplication. And 298.15. There we go, Kelvin. And boom, there we go. So now that we have all this written down, everything's filled out, we need to determine what units we're trying to find. We know we're trying to find moles, but just in case we made a mistake, let's go through, let's cancel out all the units. Alright, so kPa is up here. Let's take this out. Now let's look down here, we have kPa. Let's divide that out. We have liters over here, divide that out. We know we have liters down here, divide that out. We have Kelvin over here, we have Kelvin over here, let's divide that out. The only thing that's left is moles. So we know that our answer is going to be in mole. Alright, so let's multiply all this together, and then I believe you get 40.3. I don't know why I say I believe, I know. You get 40.3. Alright, so there's your answer. Unfortunately, the question is asking for the mass, not the mole. It's not asking for the mole, it's asking for the mass. So, let's use the knowledge that we have now. We have this 40.3 moles. We need to use something called the molar mass that you're very familiar with at this point to determine. So let's think about it this way. So let's say it's 10 grams per mole. We have 40.3 moles. Well, we know it's just going to be these two multiplied by each other, and that's going to give us the amount of grams. So let's do this in terms of unit analysis and make sure that all our units are going to be correct when we do this. Because we don't want to make any mistakes. We don't want to get docked these silly marks. Alright, so here we go. Take out the brush. Alright, so let's look in our data booklets. We need to find the molar mass of nitrogen 2. If I can find my cursor. There it is. Okay, so N2. You know the molar mass is 14.01 grams per mole. But we also know that it's N2 because it's diatomic and it's only found in nature in this way. So we need to take this, just multiply it by 2, and now we're going to get 28.02, and this is grams per mole. This is the molar mass. So let's think about this. If we have 40.3 moles, then how many grams are we going to have? It's obvious if there's 28.02 grams in 1 mole, how many is there going to be in 40.3? Let's find out. Let's write it out. We have 40.3 grams, or moles, my bad, of N2. This should be uppercase. N2, and we want to find out, we need to cancel out units. So we're trying to get rid of this mole, and we're trying to keep our grams. So we know that units divide each other out. So if this is on top, the mole should also be on the bottom. So we know in 1 mole, there's 28.02 grams. So let's look at this. These divide each other out when you're doing it. And 40.3 divided by 1 is just 40.3, which is now multiplied by 28.02 grams. So we know our final answer is going to be in grams because it's the only unit left. So we multiply this together and it gives us 1,129.206 grams of our nitrogen 2. And now that we have this answer, you would think you're done, but make sure not to miss the crucial step of significant digits, because this is just silly marks to lose. This is not what you want to be, getting docked that 1 mark for on a test and losing some marks because you put your answer wrong. So if we had, let me write out the number again, 129.206 grams and 2. Okay, so if we have this, and we look back at our question, we need to determine how many sig digs. And because there's multiplication, we're going to use the lowest amount of precision. So looking at this, we have 4 digits, 5, we have, this will be 3 at one point, but this was not used in our calculations, so this doesn't count at the moment. We have 1,000, and we have 100. So this is obviously the lowest, so it's going to be 3 sig digs. So just make sure you write this out, or if you're looking through a question and you write out all your variables, you can write right at the beginning, and then you know how to convert your answer at the end. We're just doing this step last, so I like to go 1, 2, 3. So we're here. In any situation, even if this number was 1,000,000, it should just be one number, decimal, another number. It's just going to be one single digit out front the decimal point always, and the rest of the digits are going to be behind. So if it was four sig digs or whatever, and you had a 7 number thing, it's still going to be 1, 1, 2, 9. There, that's your number, right? All right. Anyway, totally beyond the point. Not that I need to teach you this, just something important to point out. Anyway, so looking at this, you have 1.12, and those are 3 sig digs. So now we need to round up for this last number. I guess it would be this number here, using this number. So we know this is a 9, and we obviously know if it's a 9, it's obviously going to go up, right? So this is going to be a 3 now. So in our final answer, we're writing 1.13 times 10. Now, how do we know what it's 10, times 10 to? Well, we know that if it was 3 sig digs, then we need to move, actually, the easiest way to put this is how many decimal places you move over. So if we move 3 to get here, which we did, all the way from 1,129, we moved it 3 places over, right? So we know that if you multiply it by 10 3 times, it's now going to be at that point. So let's write times 3. So this will be 1,130 grams of N2. This is our final answer. Hopefully this tutorial is not too confusing. This is a very simple unit, and you should have no difficulties with it. But thank you for watching. I hope you guys enjoyed it.